Hi, folks. This is Rongyu. I'm going to present our work, Entropy Meets Multi-Hypothesis for Post-and-Shape Recovery. This is a joint work with Linlin Yang and Angela Yao. We are from Computer Vision Machine Learning Group at NUS SOC. Before we start, I would like to keep these questions in mind. Why do we want multi-hypothesis? How does multi-hypothesis connect to entropy? What are entropy effects and how to evaluate? There are common ambiguities in the task of predicting human simple and hand-manual parameters from single-view RGBs. For example, depth in the left and occlusion ambiguities in the right. To this end, we propose a gold criteria predicting accurate poses on 2D visible, while diverse and visible on 3D occluded key points. There are not many explicit one-to-many correspondence data in the current data set for model to learn. Thus, the model will degrade into deterministic, as shown in the second rows in the figure. On the other hand, weak supervision is easier to obtain, but MLE totally failed in this case. If there's no data, what can be used? The answer is knowledge. To mimic how the human do, we are guessing occluded while lifting into 3D to check 2D reprojection and if the pose is feasible. Fortunately, there are many off-the-shelf general priors of feasible poses. This does not ensure diversity. Don't worry, there are another type of knowledge about the occluded. That is, our human knows there are many possible positions without more cues. This is also called maximum entropy on uncertain principle. Our intuition behind this is use this on-hand knowledge and weak supervision to define the targeted distributions to alleviate the reliance on strong annotations. As an illustration, what we have is ij1, and what we want the distributions to cover ij1 theta 11 to ij2 theta t2. Hereby, we propose a probabilistic framework named the multi-hypothesis entropy. We first define data distributions by 2D reprojection and feasible prior knowledge. We use a generative normalizing flow as model distributions and then apply reverse KL divergence to pull model distributions to both data distributions. It derives 3 terms, including conventional reconstruction, prior, and missing entropy. The essential entropy encourages meaningful diversities when it can, while visible key points is mainly supervised by the other 2 terms. Here is a framework. We first extract the image features and then send to the normalizing flow to sample theta. We check the theta by computing 3 losses: reconstruction, prior, and entropy. We apply accurate Laplace for visible key points and diverse uniform for invisible key points. In the perspective of our framework, we regard ProHMR as a variant of no entropy, and WS3DPG uses scans which is hard to optimize. CMVAEs uses less expressive distributions compared to our normalizing flow, while others is purely data-driven. To show the effects of the 3 terms, we conducted toy ablation studies. In the first column, without entropy, the model missed 2 modes. In the second column, without the reconstruction, the modes become diffuse. In the third columns, when changed to different priors, the learned modes becomes different. As for evaluations, the existing work only evaluates best hypothesis accuracy. According to golden criteria, we propose an accuracy on visible key points and the diversity metric and the conditional diversity on accuracy, which is the ratio between the most certain and uncertain. As a result, our methods achieve accurate and diverse results, which meets more criteria more. Moreover, our methods can also be used in strong supervised settings. Our methods outperforms existing SOTAs by a larger margin in more ambiguous data sets. Our methods can also be used for post-selections, for example, hand-object interaction grasp and multi-view fittings. It can serve as a better prior. In summary, we propose a probabilistic framework for a partial weak supervision setting, makes use of knowledge and derives a missing entropy. The flex framework can incorporate more consistent and ambiguities for meaningful diversity only on uncertain. Besides, we promote a comprehensive multi-hypothesis evaluation. We also like to acknowledge these people's helps for this work. Thank you for attention.